Hello everyone, welcome back to the lectures on Introduction to Multi-Agent Systems. In today's lecture, we'll continue our discussion on incidence matrices. Now, incidence matrices, owing to their construction and the definition, have many interesting properties. This will be the focus of today's lecture. So let's get started. Before we start discussing the properties of incidence matrices, let us start with an example. Let us look at the diagraph that is shown in this figure. This is the same diagraph that we looked at in the previous lecture. Let's quickly write up some of the straightforward things that we can see from this diagraph. The number of nodes here is equal to 5, and the number of edges is equal to 6. Hence, the incidence matrix will have a dimension of 5 cross 6. So let's write up the incidence matrix now. So the vertices are just 1, 2, 3, 4, and 5, and there are 6 edges. And E6. Okay. So the first edge starts at 1, ends at 2. E2 starts at 4 and ends at 2. E3 starts at 1 and ends at 3. E4 starts at 3 and ends at 4. E5 starts at 3, ends at 5. And the last one, E6, starts at 4 and ends at 5. So this is our incidence matrix. Now, let us look at the first column here and add up all of its entries. Meaning, if we write, let me use a different color here to write the summation. If we now write B, the first column, but we vary all the rows, BI1, as I varies from 1 to N. This, as you can see, adds up to 0. Meaning the column sum of the first column that we see here, this sum is equal to 0. If you observe, the sum of entries is 0 for every other column as well. If you see here, this is 0, this is 0, and similarly, this is 0. The last one also adds up to 0. So why does it happen here? Is it only true for this particular diagraph, or it will hold in general? As you can see, whenever we are writing the incidence matrix, every column tells us where the particular edge associated with that column, where does it start and where it ends, meaning only 2 of the entries can be non-zero here. Not only are they non-zero, one of the entries is always equal to 1 and the other entry is always equal to -1. Because of this property, the sum of entries of every column in every incidence matrix will always add up to 0. So this brings us to the first property. So consider a digraph G with a vertex set V and an edge set E without any self loops. Further, let the incidence matrix associated with the digraph G be B n cross M, where n is the number of number of vertices or nodes, and M is the number of edges in the digraph. Then the property that always holds is that the column sum adds up to 0. How do we add up let's first write B. How do we add up all of the columns here? We multiply it with a row vector consisting of all ones. Let's write the complete version of the incidence matrix, which is B11, B21 up to Bn1. And this will go up to B1m, B2m, up to Bnm. Okay, now since there are n number of entries here, the dimension of this has to be equal to n here. And this we know adds up to 0. How many entries will be there on the right hand side? It will be the same as the number of columns, obviously. Hence, the number of zeros will be, so let's write it. This matrix here will have a dimension, this is a row vector, will have a dimension of 1 cross n. And this row vector here will have a dimension of 1 cross m. And this, as we already know, has a dimension of n cross m. To sum it up, we can write 1n, which will be the column vector consisting of all entries is 1. We take a transpose of it, get the row vector, multiply it with b. The RHS will have the 0 vector, but the transpose of it. Meaning, whenever we take any digraph, we know that this always holds. So we can quickly write up the reason for this as well. This holds because every column of P has only 2 non-zero entries. One and -1. That's it. That is the reason why it holds. Okay. With this, we are done with the discussion on the first property. Now we'll look at or move towards the second property that is probably slightly more important for us. But before we do that, we'll first start by writing a very interesting aspect about the incidence matrix. Note that an incidence matrix B can be defined even for an undirected graph. So how is it possible to define the incidence matrix on undirected graph? The answer to that is, let's write it. To do so, we simply make the given undirected graph as a directed one by arbitrarily assigning directions to all the edges. Hence, we can take just any undirected graph, add directions to all of its edges, and then write up the incidence matrix for the now directed graph. Again, let's look at a quick example. Let us consider the undirected graph that is shown here. What we can do is, we can create a directed graph out of it simply by assigning the directions to the edges, some directions arbitrarily to all of the edges. So let's do that. Say this is the directions that we assign to the edges. Now let's quickly write up some information that we see here. N, the number of vertices, is equal to 4. M, which is the number of edges, is equal to 5. Hence, the dimension of the incidence matrix is 4 cross 5. And what will be its value? Let's write it. We have 4 edge vertices and 5 edges. For the first edge, we see that it starts at 1 and ends at -1. The other two entries are 0. E2 starts at 1, ends at 3. The rest are 0. E3 starts at 2 and ends at 3. The rest are zeros. E4 starts at 2, ends at 4. And the last one is E5, which starts at 3 and ends at 4. So this is the incidence matrix that we can construct for a undirected graph. Obviously, a fact that follows here is, let's write it, yet another NB. Consider an undirected graph G with a vertex set V and edge set E. It is possible to construct multiple digraphs using G as the edges can be assigned directions in multiple ways. So let us gray this out. this part, as it is only important for us to remember that it is possible to construct multiple digraphs using G, which further implies that B associated with the original undirected graph G is not unique. Hence, we cannot say that there's just one instance matrix that is associated. There could be multiple. Just to give an example, here, suppose we reverse the direction of edge E2. Let me now make the direction of E2 in this manner. Then what would happen is this entry becomes +1 and this becomes -1. And as before, the rest continue to be 0. Again, this is yet another incidence matrix associated with the same undirected graph. With this, we are now ready to state our second property. Again, let us consider an undirected graph G with vertex set V and edge set V with n being equal to the cardinality of V and m being equal to the cardinality of the edge set E for some directed version or for some digraph associated with G. Suppose the incidence matrix is given by V, which will always have the dimension of n cross m. So this is what is given to us, an undirected graph G and some directed version associated with the same undirected graph G. Now, for that directed graph that we have, we can write up an incidence matrix. And that incidence matrix we denote as B. Interestingly, then the Laplacian of the undirected graph G is given by L equals B W B transpose. Where W is a diagonal matrix of edge weights. And has the dimension m cross m. So let's look at this expression one more time. What it does is, the left-hand side of this expression has the Laplacian of a graph. But which graph? It has the Laplacian of the undirected graph. On the right-hand side, we have the incidence matrix. Now, this incidence matrix is associated with some digraph that we constructed using the undirected graph. What does this imply? This implies that it doesn't matter which version of the directed graph we constructed using G. For every incidence matrix that we can associate with G, this expression holds. We can always construct the Laplacian of the original undirected graph. Let us look at it with an example. We can consider the same example that we saw here. Suppose we have this example. Now let's write what the Laplacian would look like. Laplacian is equal to d minus a, and this has 4 nodes, hence it's a 4 cross 4 matrix. So I'll directly write up what the expression would look like. So node number 1 has a degree of 2 and has edges E1 and E2. Similarly, node number 2 has a degree of 3 and is adjacent to every other node. The same holds for node number 3 as well. Node number 4 is adjacent to nodes 2 and 3. Hence, it has a degree of 4. And this is what the entries of the Laplacian would look like. What do we need to verify now? We need to construct some directed version of the graph and see if the Laplacian that we wrote up here is actually related to the incidence matrix of the directed graph. So let's get started. Let us construct this graph with the edges given directions in this manner. Again, we have already seen the incidence matrix for this particular graph. E4 and E5. This is 1, 2, 3, and 4. E1 is incident with 1 and 2, and E2 goes from 1 to 3. E3 goes from 2 to 3. E4 goes from 2 to 4. E5 goes from 3 to 4. So this is our incidence matrix. Let us now do the multiplication of B, W, and B transpose. So notice that we have not assigned any H weights here. Hence, we have to consider the H weights to be equal to 1. So let me write it here. So this is what the incidence matrix looks like. And W is simply the identity matrix because it's a diagonal matrix with all of its entries being equal to 1. So let me not write it at all. And what I'll write next is B transpose. Then the transpose is given by 1, 1, 0, 0, 0, minus 1, 0, 1, 1, 0 again, 0, minus 1, minus 1, 0, 1, and 0, 0, 0, minus 1, minus 1. Okay, this is obviously an M cross N, meaning 5 cross 4 matrix. This is 4 cross 5. And what will this product be equal to? Let's see. What we can clearly see is this will obviously be a 4 cross 4 matrix. But what will it be, its entries? Its entries are equal to, let's calculate. Multiply these to get the first entry. This comes out to be 2. Then we multiply the first row with the second column of V transpose. And what we get is -1. Similarly, we get this third entry of the first row of the product also equal to -1. And the last one is equal to 0. Similarly, let's look at the second row of B and the first column of B transpose. So this product is obviously equal to -1. The second entry here is equal to this times this, which now adds up to 3. Similarly, the second row with the third column, now you can see this adds up to -1. In a similar way, we can easily calculate that the last entry is equal to -1. So we can keep on repeating this, and what we will get is the next entry here will be equal to, again, -1, -1, 3, and -1. And the last one is 0, -1, -1, and 2. And let us observe this. BWB transpose gives us this matrix, and this matrix is exactly the same as the Laplacian of the undirected graph. Note that we simply chose any arbitrary directed graph constructed using the original undirected graph, and this relation still holds. So I hope you now understand what the property means. So now let's try to quickly look at the proof of this. Why does it hold? Let's start with the proof. In the proof, we start by considering some undirected graph. Let's write it. Consider an undirected graph G given by a vertex set V and edge set E. Let us assign directions to all the edges of G to get a digraph G prime. Let the incidence matrix associated with G prime be simply B, which will have a dimension of n cross m, where m, let's start with n is equal to the cardinality of the vertex set, and m is equal to the cardinality of the edge set. So this is a framework that's given to us. Now, with this, let us start computing BWB transpose and see what we get. BWB transpose is simply given as the product of B11, B12 going up to B1m, and there are n edges, so Bn1, Bn2 going up to Bnm. W is a matrix, is a diagonal matrix of all edge weights. There are m edges, so 0, W2, 0, 0, 0, going up to Wm. And the last matrix that we have here is simply the transpose of P. given by B11, B12 up to B1M. We can also write some arbitrary column here as BJ2 going up to BJM. And then the last one would be BM1, BM2 going up to BMN. This is N. Now, just for completion, let me add the ith row here. BI1, BI2 going up to BIM. Okay, so let's quickly observe a few things. As before, this matrix has a dimension of n cross m. This has a dimension of m cross m. And this here has a dimension of m cross n. And we are interested in calculating all of the values, all of the entries of this product. To do so, let us observe first something very interesting, which follows quite directly from the construction. Now the matrix B, when multiplied with the matrix W, let's remember that W here is a diagonal matrix. When we multiply this with B, what will happen is the first diagonal entry, W1, will simply scale the entries of the first column of B, meaning what we will get here is simply W1, B11, W1, BI1 going up to W1, BN1. Similarly, the second diagonal entry will scale the columns of the the entries of the second column of B. So this will simply be W2, B12 going up to W2, BI2. And the last one would be W2, N2. Similarly, the last diagonal entry here will simply scale the entries of the last column of B, which will give us this WM, B1M, WM, BIM, and the last entry here would be WM, BNM. And again, we'll simply write the transpose of B given by B1M up to BJ1, BJ2 to BJM, and the last column given by BM1, BM2, and BMN. So this is a neater form of BWB transpose. And what we are actually interested in is in the ijth entry of BWB transpose. So let's write it. The ijth entry, denoted as this, will simply be the product of the ith row of B times W multiplied by, the jth column of B transpose. So meaning, let's write it. This implies that BWB transpose, its ijth entry is simply equal to W1 times BI1 times BJ1 plus W2 BI2 times BJ2 going up to WM BIM times BJM. Okay. Now let's calculate what would be the value of this sum. So of course we can write it in a slightly more concise way as WK BIK times BJK, where K varies from 1 to M. Let's now try to understand what will this be equal to. So what we are looking at here, the entry, we are trying to figure out what will be this product BIK times BJK. What does this signify? We also have a WK multiplied here. Now this implies we are interested in the edge starting at node I and ending at J. We can denote it as something like this, I to J. Note that it could be the other way around as well. It could very well have started at J. Let's write it, or J here, or I, which would give us a different form. I, J. Okay. So what we're trying to figure out is the only way this product here is non-zero if either there is an edge from I to J or if there is an edge from J to I, in which case this is equal to this term is equal to WK, which is nothing but the edge weight. We can write it as AIJ, suppose, times 1 and minus 1, meaning this is equal to minus of AIJ. That is exactly what it is equal to. In order to evaluate this value, we in fact have to look for edges between nodes 1, node I and node J, meaning suppose there exists an edge from I to J with some this being the entry of the adjacency matrix, the corresponding weight. Only if there exists some edge from I to K, only then this entry here will be equal to, will not be equal to 0, will be non-zero. Meaning in that case, there exists some K between, in the set 1 to M, at least one of the edges, such that WK BIK times BJK is in fact equal to WK, which is the weight of the edge. We can write it as AIJ, and then the other two entries will be 1 times minus 1, which simply becomes equal to minus AIJ. If there does not exist, if I and J are not adjacent, there's no edge, then this product WK BIK BJK is simply equal to 0. So here, please remember that we have considered I and J to be distinct. I and J, or rather, I is not equal to J. Only then we are looking at the possibilities of having edges between them. And so if there is no edge, if I and J are not adjacent, then we say this product becomes equal to 0. So meaning now we can write the following. BW B transpose. Its ijth entry given by summation of k going from 1 to m, wk, bik, bjk. Without loss of any generality, we can write minus of aij, where if there does not exist an edge, aij is simply equal to 0. So this is what happens when I is not equal to j. Now, what if I is equal to j? Let's consider that case. Meaning, in this product, for I and j to be equal, we are now looking at the diagonal entries here. Meaning in our product, we consider now entries in this manner. Let me borrow this matrix and write it here. So if I and j were to be equal to 0, we are specifically looking at the products in this manner. Sorry. The first row here getting multiplied with the first column will give us the first diagonal entry. Similarly, the second column getting multiplied by the second row of B transpose will give us the second diagonal entry, so on and so forth. And the last diagonal entry will simply be the product of the last row of B times the last column of B transpose. Meaning in general, now we are interested in BII, meaning the diagonal entries. So the expression of the ith diagonal entry is given by BW B transpose II is simply equal to, we can write it for the ith row, W1 BI1 squared plus W2 BI2 squared going up to WM BIM squared. Notice that in this expression, we are considering all of these, since we are looking at BI1, BI to 2, BI to M, which implies we are considering all the edges starting from I, node I, meaning this summation is simply equal to the degree of node I. Hence, we can write that BW B transpose, its ith diagonal entry, or we can simply write the iith entry, is simply equal to summation of all of the outgoing edges from I, meaning A, I, J, where J now varies from 1 to N. So now, what are the two expressions that we have? So this is the first expression. And the second expression is BW B transpose when I and J are not equal. So we can write it here, J not equal to I. This is simply equal to minus Aij. By definition, we saw in the previous set of lectures, in our previous topic on Laplacian, we saw that this is exactly the expression of a Laplacian matrix. Hence, thus, this implies that BW B transpose is equal to the Laplacian matrix of the undirected graph G. Okay, so this was the second property that's an interesting one to discuss. So this would imply that B transpose is equal to the Laplacian of the undirected graph G. So why is this the Laplacian of the undirected graph? Because it doesn't matter here. If we see, it doesn't matter in this expression. It doesn't matter if the edge is from I to j or j to I. This entry is still equal to either minus aij or aji. It doesn't matter. In both the cases, the entry becomes non-zero. That is why this gives us the Laplacian of the undirected matrix. With this, we will end today's lecture. In the next lecture, we'll look at some more properties associated with the incidence matrix. Thank you.